All right, let's start to talk about waves in Chapter 17. We know that there's many types of waves. Typically a wave, say for example a transverse wave, we create a pulse and then the pulse travels through the medium. And you can actually watch the wave oftentimes, like an ocean wave, or take a slinky and you make a pulse. You can actually watch that wave travel. But if we're really careful, we can actually control this and make the pulse that we're dealing with move in a direction so that when the wave comes back and moves forward at the same time, it actually looks like the wave is no longer moving. What I mean by that, if you watch a pulse travel through it, you can actually see the velocity as it moves through the medium. A standing wave, however, moves, and it just kind of, it's not that it's not moving up and down, but it's not moving forward or backwards. Well, in actuality, it is. It's moving forward and backwards at the same rate, which causes the wave to appear to just be moving and oscillating in place up and downward. So if we look, we'll demonstrate this shortly. We can create a standing wave, and the first wave, we call this the fundamental, and also known as the first harmonic. So we have the fundamental, or first harmonic, and basically all it is a wave. It has two nodes either end and then an antinode in the center. I call it a one hump type wave. So if we look at this wave, we can see that the wave is confined by this length right here from here to here. If this was a guitar string, doing, and we pluck it, on the guitar, at the lower end you have the bridge, and at the upper end it's called the nut. So the vibration part of the string is between the bridge and the nut. This is that length right here. That would be the length. Not the whole length of the entire string, just the part that's vibrating, and we call that L. So if we look at this, you notice that the length of the string is related to, well, the wavelength. So if I look at a wave, I see the waves go up and down like so, along the midline like so. If we start here and then end up here, this is one wavelength. Now, when we look at this, it goes from the midpoint up to the peak and then back down. So when I look at this fundamental, it's really only half a wave. So from here to here is a half a wave, and that corresponds to the length of that. So when we write L is equal to 1/2 a wavelength for the fundamental, this is true. Okay, we can also do this in terms of velocity. We know that V is equal to F lambda. All right, if we solve this for the frequency, for the wavelength, we know that this is going to end up being V divided by F. So in this formula, we can also do it in terms of the frequency and the velocity. So we have 1/2, and instead of writing lambda, we can write V divided by F. And then if it's half, the 2 goes in the bottom. So this is a velocity and frequency version of the same formula. Depending upon the situation, you'd use either one of these two formulas. All right, now let me try to demonstrate a standing wave. So we're going to take a spring, and I happen to have the spring right here, and I'll pivot it around like so. And if we could look, see if we can actually see the spring moving up and down. And we kind of look this direction. All right, I don't know how this is going to work out for you, but it's worth a try. So I take the spring and I move back, and I'm going to create the fundamental, which seems very simple. So I'm going to take it and I'm going to pulse it, and I'm going to pulse it and time it just right so that the pulse traveling back is equal to the pulse in the front, and then we end up with this situation right here. And we have a single wave right here, standing wave. My hand is where the node is, the antinode is in the center, and we're demonstrating a fundamental. So it's waving up and down like so.